So this is test 3 review. Number 1 is asking to find the first order partial derivatives for the function. Partial f with respect to x. So we have something squared, so the derivative, we're going to bring down the 2 and copy the inside. And then the inside is when we actually just look at x, y is a constant. So this term has x in it, we're holding y constant, so x to the 4th, bring a 4 down. So that's 5 times 4, x cubed, y cubed. And then we can kind of clean up 2, 5, and 4. 40, x cubed, y cubed. And that's the partial of f with respect to x. And do the same thing for y. First part stays the same. Now the 3 is going to come down. Oops. So the main thing is to find 40 and 30. So that would be B. So then number 2, again, we're going to find the first order partial derivatives. And this time we have a square root in the denominator. So I'm going to rewrite that as a negative 1/2 power. So it comes down. And the derivative of x squared is 2x. And I have a 2 and a 2. So that's going to be x, and then x squared, or negative, to 3/2, the denominator. And then y is going to be the exact same. I won't redo it. Oops, y. Not a 2, so A and B. Again, not a 2, so it's not D, so it has to be C. So finally, the second order partial derivatives. So we got to find the first order before we can find the second order, and then we're going to have the second order mixed partials. So we're going to have 2x minus the derivative of the exponent is the exponential times the derivative of the exponent. And so we can take the derivative again. And while we have this one, I'll just go ahead and take the mixed partial. So now I'm looking at this and taking the derivative of this with respect to y. And then we'll do the y partial. In the second order. And then the mixed partial. And you notice the mixed partials match. They're equivalent. So this one, 2 plus, no, 2 minus. That's the mixed partials. Or the mixed partials. And then we got that for that, so it's D. So then number 4. Okay, so number 4, same thing. And again, the mixed partials match. So it's not A. I seem to want it factored. It's not D. Oh, wait, there's a Y in common. So, let's see. And now 5, we have 3 variables. So we're going to find all 3 partials. It's just the first order. So it's not A. It's not B. It's not C, so it has to be D. Let's look at Z. Y squared 2x Z. So 5 is D. So number 6. That's supposed to be an exponent. So the derivative of sine is cosine. So that's not B, not C. I need a Z, so it's not A, so it has to be D. But just to make sure, we need Y. Yeah. So 6 is D. So number 7 is asking to determine whether this function satisfies the Laplace equation. Laplace is the summation of the partials. must equal 0. So we're going to find all the second degree partials. So if we added up the second degree partial, the second order partial, whatever, that's not going to equal 0. So this does not satisfy Laplace's equation. So 7 is A. No. And number 8, I think it's wanting you to do the chain rule for partials. It's not that bad if you just substituted in for P, Q, and R like into the equation and then took the partials. So number 8. So P squared is x squared, y squared, minus y to the 4th, minus minus z, xz. So then partial respect to x. Okay, so this one's only asking for the partial with respect to x at 5, 3, 2. So 2 times 5, 3 squared minus 2. That's 10 times 9 minus 2 is 88, which is D. So number 9 is saying use implicit differentiation to evaluate the derivative at a given point. So for this, I have to find partial of z with respect to y. So the whole time I'm going to hold x constant. So I'm going to start by simplifying the log. So now I have y and z together, so I'm going to use the product rule. So I'm going to first take the derivative with respect to y. So that just leaves me 1 over y. And it's going to be the same thing for z, except now I have the, oops, it's supposed to be z. I have the differential. And then the derivative with respect to x is 0. With respect to y, with respect to x, z, so now I'm going to get my terms that have the partial, or the partial differential together. I'm going to move it to the right side. So now I can get the partial is 1 over y minus all this stuff over this stuff. And now I have to evaluate it at 7, 1, negative 1. So 1 over 1 is 1 minus 7 e to the 7 times 1 plus negative 1 squared, it's 8. 2 times negative 1 is negative 2 e to the 8 minus 1 over negative 1, that's plus 1. And that is A. Number 10. Some story about stuff. P equals V squared over R. And it tells me this equation. Which is basically the chain rule. So when you take the derivative of p with respect to t, you have v and r both are functions of t. So when you take the partial with respect to v, you also have to do the derivative of v with respect to t, and same with the resistance. So then I actually need to find the partial of p with respect to v and the partial of p with respect to r. So v, that's just going to be 2v over r. For r, it's negative v squared over r squared. And then I'm going to put these into this equation, and it tells me that dr dt is 1 ohm per second, and dv dt is negative 0.01 volts per second. And R is 4 ohms and V is 2 volts. So I want to evaluate all of this. That's going to be 2 times 2 over 4 times negative 0.01 minus, that's negative, v squared, that's 2 squared over 4 squared times 1. So that's 1 is negative 0.01. That is 1/4 times 1, so that's 0.25. That's negative 0.26, which is A. Then 11 says find the gradient of the function. At 999. So the gradient is just a vector of all the partial derivatives. So that's the x component, the y component, the z component in the ijk direction. So the partial with respect to x would be 2x over all of that. The y component, 18y. And the z component, and now we get to evaluate it. So that's 18 over something that I'll type in a calculator. 18 times 9. Okay, and 405 was 5 times 81. Which is 5 times 9 times 9. 90. 9 times 9 times 2. So 9, 9 and 9. 9, 5. So I'm left with 2 over 45i, 2 over 5j, 2 over 9k. Which is C. Number 12 says to find the derivative of the function at a given point in the direction of A. So I'm going to go ahead and find the gradient of f. It's 6, -2, 7. And then there's some vector u that's in the direction of A. So u is the unit vector. So magnitude of u is 7. No, I'm gonna call it u. Okay, so there's some vector. So now to find the derivative of the function at a point in the given direction, I'm going to dot f with v, or u, I don't, whatever. That's 30 minus 14, that's 16 over 7, which is A. So now 13 says, find the direction in which the function is increasing most rapidly at the point 2, 1, 1. So I'm going to find the gradient. And then evaluate it at 2, 1, 1. So 1 square root of 2. It's 2 square root of 2. And 2 square root of 2. And then the magnitude of the gradient is the square root of 6. So then the gradient divided by the magnitude of the gradient or which the answer is D. So number 14 is asking to find the derivative of the function at the point in the direction at which the function increases most rapidly. And the point is -7, 7, -7. So I need to find the gradient. So with respect to x, that's 1 over y minus z over x squared plus respect to y and then with respect to z so now I need to evaluate. So it's 1 over 7 minus -7, so +7 over 49. It's positive. That's gonna be negative. It's negative. Negative. So that's 1/7, so that's gonna be 2/7. That's 1/7, that's gonna be 0. That's 1/7, that's -2/7. Okay. So the direction it's increasing most rapidly, I need to find, well, that's the gradient of f at the point. Now I need to find a unit vector in this direction. So I want to find the magnitude of f, or the magnitude of the gradient. So it's the same component, so it's 2/7 square root of 2. So then the unit vector in that direction is going to be square root of 2 over 2 I minus square root of 2 over 2k. So now I'm going to dot the gradient and the unit vector and the direction to make sure that, like, I'm getting the derivative in that direction. And it's increasing most rapidly. If it was decreasing, it would be the negative. But we're trying to find, you know, increasing most rapidly. So then I'm going to dot 2/7, negative 2/7. That was the gradient. And that was the unit vector. And that is B. So number 15 is saying write an equation for the tangent line to the curve at the point. So I'm going to take the derivative. Put 2 on both sides. So dy dx is equal to negative 9x over 100y. And then I need to evaluate at this point. That's negative 9. So square root of 2, square root of 2 is gone. So we get negative 3/10. So I have y is equal to negative 3/10 x minus 10 square root of 2 plus 3 square root of 2. And none of the answers are in this form, so I have to do some algebra to get it into the form I want. So if I divide by 3, I'm going to have y over 3 plus x over 10 is equal to square root of 2, which is a. So 16 is saying to find the derivative of the function at a given point in the direction of a. So it's not telling us the most rapid or whatever, it's actually giving us a direction to find. So it's the same process, it's just now it gives us a vector to use. So 16. So I'm going to find the gradient of f. And then I need to evaluate it at this point. Get some ridiculously large number. And then I have A, so I'm going to find the magnitude of A. So then U is the unit vector in the direction of A. And you dot them. And you get A. So 17 is saying find the equation for the tangent plane to the surface at a point. So I'm going to set it equal to 0. And find the gradient. So then I'm going to evaluate the gradient at the point. And I get the vector 32, 21. And the equation for the plane is the gradient in the x direction times the point in the y direction z direction, and it's equal to 0. So I have 32 x minus 2, 20 y minus 1, 1 z plus 42. And when you simplify this, you get 32x plus 20y plus z is equal to 42. Which is B. So 18 is asking to find all local extreme values. Local max, local min, or saddle point. So a saddle point is when you have something like this. Like in the x direction, maybe you have a parabola opening up, but in the y direction, as it crosses, it's opening down. And so it looks kind of like a Pringle. I wonder if I can draw a Pringle. But it's kind of curved right here, curved down, while this section is curved up. It's looks kind of like a saddle. So 18 So I want to find the partial in the x direction. And it's concavity. Concavity, so I'm going to have to worry about the second derivative. So it's positive. The y derivative. So, since they're the same and there's no mixing up of the positive, negative, there's no sign difference, you don't have a saddle point. So I'm gonna look at the second or the first derivative to find the critical points. So x is -5, y is +5. So -5, 5 is a critical point. So if I evaluate get 25 minus 50 plus 25 minus 50 plus 8. So 25, it's 50. That would cancel with that. So I have a -42. And the second derivative is positive, so it's opening up, so I have a minimum. So 18 is B. So 19. So I'm doing the same thing. I need to find the extreme values and determine if I have a max, min, or saddle point. Oops, x, y. Oops. Looking back at 18. So this one, both the second derivatives are equal to 0. So I'm going to look at the mixed partial. Is 2. So a way of determining something, a classification of a critical point, is to look at the second derivatives. Kind of crooked. You multiply the second derivatives of in respect to x and respect to y, and then you subtract the mixed partial squared. So if it's greater than 0, then you have a max or a min. If d is less than 0, you have a saddle point. And here I have 0 minus 4. It's 2 squared, so we have a saddle point. So the critical point is going to be at negative 5 halves, 5 halves. It's a saddle point. So 19 is A. So number 20, I'm doing the same thing. I need to find max, min, or if it's a saddle point, settle, well, I said settle, okay. I'm gonna write this out better. Oh, minus 5. And then the second. Might as well take the mixed partial. Okay, so now I need to find a critical value. So I'm going to look when the first derivative is equal to 0. Oops, x squared. So 10xy, so that means that 5y squared is equal to 5x squared. So my critical point is at 0, 0. And if I look at the second derivative, if I put in 0, 0, I'm going to have that the second derivative is 0 in both directions, and the mixed partial is 0. So when I go to calculate when I go to calculate D, I'm going to have 0 times 0 minus 0. That's going to be 0. It means the test is unconclusive. Inconclusive. Whatever. So that is B. You're going to have to find a different method because it didn't work. So 21, judging from part A alone, it's going to be a long problem. So I'll take the first partial with respect to x. The second, where do you write that? It's 4x, x squared minus 100. So then the second derivative is going to be 8 x squared minus 100. No, just 8x squared. Plus 4 times x squared minus 100. It's basically the same thing. Oh, that's 8. And then the mixed partial is 0. So to find my critical values, I'm looking at the first derivative is equal to 0. So I'm going to get x as 0, 10 and negative 10. Y is 0, 4, and negative 4. So okay, so when I go to evaluate these in F, I get 10, 256, 256, 10,000, 256, 0, 0, 256, 0, 0. So I have my max. My 4 min, and then I have these 4 points that are most likely saddle points. So I'm gonna go and test them in the second derivative. Mm, 0, 4. Negative 10, 0. Oh, I forgot about 0, negative 4. So basically every point when one of the variables was 0, I have something going on. Possibly a saddle point. So at 0, 4, I get negative 400 and 128. And the same for 10, 0. No, same for 0, negative 4. Negative 400 and 128. And then at 10, 0, I get 800 and negative 64. 800 and negative 64. So a saddle point is when the derivatives are opposite sign. So you have D and here the mixed partial is 0. So when these are opposite sign, you're gonna have a negative. And when D is less than 0, that is a saddle point. So when these are opposite sign and the mixed partial is 0, like in this case, you have a saddle point. So out of all my points, 0, 0 was the max. 10, 4, 10, negative 4, negative 10, 4, and negative 10, negative 4 were the min. And then I had saddle points at 0, 4, 0, negative 4, 10, 0, and negative 10, 0. And that is A. So number 22 is saying to use the least squares regression to find, the regression line. So in the calculator, you're going to press Stat, Edit, and you're going to put the independent variable numbers into the X, into L1. And then the dependent into L2. And then second, quit, and then go back to stat, arrow over to calc, you want number 4. And yes, you put your x's in L1, y's in L2, and calculate. And you get that the slope is 7.97 and the y-intercept is negative 13.54, and that is C. So number 23 says find the extreme values of the function subject to the given constraint. When you have a constraint, you're going to have a Lagrange multiplier. And if you only have one constraint, you only have one Lagrange multiplier. If you were given 2 constraints, you'd have 2 Lagrange multipliers. And so forth, and it gets more complicated. So number 23. So I'm going to find the gradient, and this is G. Gradient of f is 16x, 8y. So you got to find some multiplier that equates the gradient of f and the gradient of g. So that gives you 16x is 2 lambda x, and 8y is 2 lambda y. So basically you have x on both sides, y on both sides, so you're going to have 2 scenarios. Either lambda equals 0, or lambda is not equal to 0. So usually when lambda equals 0, you get 0, 0, and it's just a trivial solution. So if lambda is 0, you're going to get x is 0, y is 0. Well, according to our constraint, that's not possible. So lambda is not going to equal 0. So if lambda is not equal to 0, I either have that x is 0 or y is 0. So if x is 0, according to our constraint, y is going to either be positive or negative 1. And the same, if y is 0, x is going to be positive or negative 1. So that gives me 2 points. I'm sorry, 4 points. 0, 0, 0, negative 1, negative 1, 0, 1, 0. So for these two, I get 4. So both of these are minimum. And then for these two, when I put it into F, I get 8. So for these two, I have maximums, and that is B. And 24. So I'm going to find my gradient. So I have y is equal to 2 lambda x, and x is equal to 2 lambda y. So if I solve for lambda, I get that lambda is y over 2x. And I'm going to put that into this equation, and I get that x is equal to y squared over x. So x squared is equal to y squared. And if I put this into the constraint, I get that 2x squared is 32 and 2y squared is 32. So x squared is 16, so x is positive or negative 4, and y is positive and negative 4. So again, I have 2 points. 4 points, 4, 0, 4, 4, 4, negative 4, negative 4, 4, and negative 4, negative 4. So I'll put this into F, and I get 16, negative 16, negative 16, positive 16. So 4, 4, and negative 4, 4 are max. And negative 16 and negative 16 are minimums. And that is C. So 25. I have 3 variables, but that doesn't really change anything. So the gradient of F gradient of G so I have 1 is equal to 2 lambda x, 2 is equal to 2 lambda x, I'm sorry, y, negative 2 is 2 lambda z. So I'm going to solve for x, y, and z. X is 1/2, or 1 over 2 lambda. Y is 1 over lambda. Z is negative 1 over lambda. So then I'm going to put this into my constraint. And I get an equation with just lambda. So if I multiply through by lambda, that's 4 over 4, 4 over 4. So that's 9 over 4. So lambda squared is 1/4. So lambda is either positive or negative 1/2. So if lambda is positive, x is 1/2. No, I'm sorry. Lambda x would be 1. Y would be 2. Z would be -2. And if lambda was negative, I'd have the exact opposite. So when I evaluate this, I get 9, which is a max. And if I evaluate this, I get -9, which is the minimum. Which is A. So 26, 27, 28 are integrals. So a double integral. So 26, I have the integral of 6x dy dx. So I have to integrate in y first and then x. So from 2 to 10, with respect to y, that's 6xy, and y is going from -6 to 9. So 9, and then I'd have a negative, I would subtract -6, so 9 plus 6, which is 15. So 15 times 6 is 90. So the integral of 2 to 10 of 90x dx. Which is 45x squared from 2 to 10. And you get 4,320, which is A. And then 27 is the integral from 0 to 3 of the integral of 0 to 5, x plus y dx dy. So I have a sum in the integrand, so I'm actually going to split it up. You could leave it the same way. I just So I get 25 halves. And 5y. I'm not gonna have an integral. So now I have 25 halves y and 5 halves y squared so that's 75 halves plus 45 halves, and that is 120 over 2, which is 60, which is B. And then 28 I could split this up like I did 27, but it's just sine and cosine, so it's not gonna be that bad. So with x first, cosine of an odd pi is -1, and cosine of 0, well, no, x would be 0, so that term would be 0. So I'd have -1 plus 19 pi cosine of y minus cosine of 0, or minus negative cosine of 0, so that's plus 1. Oh, that's negative 1, so that's positive 1. So I have the integral from 0 to 6 pi of 2 plus 19 pi cosine of y. So I'm going to have 2y plus 19 pi sine y from 0 to 6 pi. And sine of an even pi, sine of 0 is both 0. So I have 2 times 6 pi plus 0. That is equal to 12 pi, which is D. And 29 is another regression problem. So we go to stat, edit. I already have stuff in there, so you go to stat, clear list. If you type second 1, comma, second 2, that's saying clear list L1 and L2. Enter, done, stat, edit. Or if you had stuff in there, you could just arrow up and it highlights L1, and then you can say clear. And then down arrow, and it clears it. If you click delete, it's going to delete the whole list, and then you have to like reset the whole calculator and do some stuff to get your L1 back. So it's clear, not delete. So the point is x is 1, 2, and 3. Y is 36, 54, and 30. So, no. Stat, calc 4, enter, I get -3 and 46, which is D. So then number 30, I have the function e to the x, y. And I'm trying to find the derivative of the function at which the function decreases most rapidly. So I'm going to find the gradient. So with respect to x, I'm going to have y e to the xy. With respect to y, I'll have x e to the xy. So at the point 0, -2, I'm going to have -2, 0. So x is 0, so e to the 0 is 1, times -2 is -2. X is 0, so that's 0. So then the magnitude of that would be 2. And to find the unit vector in the direction where it's decreasing the most rapidly, it's negative the gradient over the magnitude of the gradient. So it's -2, 0, divided by the magnitude 2, so the unit vector in the direction is 1, 0. So that's the unit vector. I'm going to multiply by the gradient at that point. So -2, 0 dotted with 1, 0 is -2, which is A. And 31 is saying find the derivative of the function of the given point in the direction of A. So this one is basically the same thing, but it's giving us a vector to look at in that direction. So the magnitude of A is 10. So the unit vector in that direction is 3/5, 4/5. So I'm going to find the gradient of F. With respect to x, I'm going to have -4, -4x minus 5y in the y direction. And then I need to evaluate that at the point -7, +2. You get -2 ninths, -5 18ths. And then we're going to dot the gradient with the unit vector. And that's me the derivative in the direction of A. you get negative 16/45, which is B. And then 32 is a integral over a region. It's a double integral of 1 over xy dA, where the region is described by xy such that x is in between 9 and 10 and y is in between 9 and 10. It's not anything different, it's just not putting the numbers on the integrals. So I have 1 over y, and the integral of 1 over x is natural log of x, absolute value, but since I'm evaluating it in a positive, so I'm just going to say natural log of x from 9 to 10 dy. Natural log of 10 minus natural log of 9 is the same as saying natural log of 10 divided by 9. Property of logs. And you subtract. You can condense it into 1 as long as the bases are the same. So then I have natural log of y from 9 to 10. So that's the same as natural log of 10/9 squared, which is D. (33). I have the integral of 0 to 1, 0 to 1, e to the 2x plus 3y dx dy. You could split it up and say e to the 2x times e to the 3y and then have two separate integrals or whatever, but, well, not two separate terms. So it's 1/2 e to the 2x plus 3y. X is evaluated from 0 to 1. So it's 1/2. If x is 1, that'd be 2 plus 3y. If x is 0, you just have e to the 3y. So then the first term, if I integrate it, I'm going to have 1/2 times 1/3, so I'm going to have 1/6 e to the 2 plus 3y from 0 to 1. And this one I'd have 1/3 e to the 3y from 0 to 1. So 1/6 e to the 5th minus e to the 2 now this is going to be 1/6 as well. So So I had 1/2 times both of these. So the first one would be e cubed, and then e to the 0 is just 1. And it'd be a negative, so that'd be positive 1. And this is b. So number 4, again, I have a double integral over an area, over a region. And the region is where x is between 0 and pi9, and y is in between 0 and pi. So that's going to be cosine of pi, which is -1. And then cosine of 0 is 1. So that's going to be -1/9 times -1 is +1/9. And then we minus another, so that would be 2/9. Then that's going to be 2/9 y from 0 to pi. So it's 2 pi9, which is d. And 35 is from 0 to 9, 0 to 10. And that's going to be 100 divided by 2 is 50. 5 times 50 is 250. Minus 30y. That's 250 times 9 minus 15 times 81. It's 1035, which is D.
And 36 is another double integral. X is going from 0 to 1, y is going from 0 to 2. So we need 1/2 plus 1/3 y to the 4th minus 3. So you get D. It's a lot of D's in a row. And then 37 says to use implicit differentiation to find the specified derivative at the given point. Okay. So 37. The point is 1, 0. So I'm going to find the derivative dy dx. So I'm going to take the derivative with respect to x. Then I'm going to solve for dy dx. Now I need to evaluate, add 1, 0. So if y is 0, the whole numerator is 0, so it doesn't matter what the denominator is. The derivative at 1, 0 is 0, which is c. So 38 is asking us to compute the gradient of a function at the given point. And so the derivative of inverse tan of x is 1 over 1 plus x squared. The derivative of a constant times x on the inside of the inverse tangent would be a over a squared x squared plus 1. And if I had the derivative of the inverse tangent of a constant over x, be negative a x squared. Negative a over x squared plus a squared. So then for the gradient, seven y over 49x squared plus y squared, and then the y So to actually compute this, I'm going to let u equal 7x over y. So that's going to give me the inverse tangent of u. So if I take the derivative, I'm going to get 1 over 1 plus u squared, but u is a function of x. So the tackle on that derivative. So u du dx is 7 over y. U was 7x over y. So if I multiply top and bottom by y squared, that would give me 7y in the numerator, and then y squared plus 49x squared. So that's how I got the x component. And then the only difference to get the y component would be that the derivative would give you a negative. since y is in the denominator. So now that I have the gradient, I'm going to evaluate at -3, -6. And that gives -42 over 477 and 21 over 477, which is -14, 159, 7, 159, which is D.